Welcome to the Explainer. Today, we're going to completely shatter a pretty massive illusion about artificial intelligence, and we'll do it by revealing the raw, unadulterated math underneath it all. If you've ever felt like AI is this, magical black box, well, this is where we finally crack it open and look at the actual gears turning inside. So let's dive right in with a rather brilliant quote from our source material by Andrea Burkhoff. He writes, "Let's start by telling the truth. Machines don't learn." It actually turns out that the term machine learning was essentially just a 1950s marketing trick. Arthur Samuel coined it over at IBM to attract clients and talent. What the machine is actually doing isn't learning in the human sense at all. It's literally just finding a mathematical formula based on data. And this comparison brilliantly illustrates the difference. Just think about animal or human learning for a second. If you learn to play a video game, you can still easily play it if someone, say, tilts your screen slightly. You just naturally adapt. But a machine learning algorithm? No way. It will fail completely on that rotated screen unless it was specifically mathematically trained to recognize rotation. It's entirely rigid to the exact data it was fed. Here is our roadmap for the explainer. We're going to systematically strip away the sci-fi hype, look at how supervised learning actually works, and then unpack the specific algorithms acting as the problem solver's toolbox. Let's move right into our first concept and establish the foundational mechanism here. To really understand the models we hear about in the news every single day, we have to look at supervised learning. We aren't creating a digital brain in a jar. We're just following a very straightforward two-step process. First, we gather a collection of labeled examples. And second, we feed them into an algorithm to build a statistical model. That's really it. It's a tool for finding patterns in spreadsheets, not a sentient being. Okay. Let's follow a single piece of data through this pipeline to see exactly how a computer digests it. Imagine you want to teach a computer to filter out spam emails. You obviously can't just hand the computer a bunch of text, right? You have to translate it. Step 1, you gather your labeled data, say 10,000 emails, each manually tagged by a human as spam or not spam. Step 2, you convert that raw text into feature vectors. And step 3, you run the algorithm to build your statistical model. The absolute crucial point here is step 2, the feature vector. A computer only understands numbers. A feature vector turns words into an ordered list of values. For example, using a bag of words method, we just check a dictionary. If the word Aaron appears in the email, we put a 1 in that column. If the word buy appears, we put a 1. If xylophone doesn't appear, we put a 0. We've essentially just translated a human email into a massive coordinate of ones and zeros. Now that we actually have numbers, let's pull our first algorithm out of the toolbox to categorize this data. Meet the support vector machine. It uses a pretty scary-looking equation, w times x minus b equals 0. But please don't let the algebra intimidate you. This is literally just a mathematical way of telling the computer to draw a boundary line. Mathematicians call it a hyperplane. We're just drawing a line right down the middle of our data, separating all the spam vectors on one side from the not spam vectors on the other. The machine's entire goal here is to optimize its math to make the margin as wide as possible. The margin is just that empty space, or the distance between the boundary line and the closest data points of both classes. By making this gap as wide as statistically possible, the algorithm ensures it minimizes mistakes on any future unseen emails you might get. Give it some breathing room, essentially. But here is where we hit a bit of a wall. An SVM is fantastic for categorizing things into distinct buckets, spam or not spam, cat or dog. But what if we need to predict a continuous specific number? Like, what exactly will this house sell for? A simple dividing line won't work for that. We're going to need a totally different mathematical trick. Let's move on and see how we tackle predicting real-world values using regression. Linear regression flips our previous goal entirely. Instead of drawing a line that stays as far away from the data points as possible, like we did a moment ago, linear regression mathematically locks onto a line that runs as closely as possible through all our training examples. It's really trying to thread the needle right through the center of the data trend. And it achieves this perfect fit by doing something called minimizing the empirical risk. Specifically, it uses a squared error loss function. Whenever the line misses a data point, the algorithm measures that error and, squares it. Why square it? Because squaring a number makes large errors mathematically huge. The algorithm is designed to panic at large errors and heavily penalize them, which forces the line to stay as close to all the points as possible.
But we have to be incredibly careful not to make our math formula too complex. Take a polynomial regression of degree 10, for example. It perfectly connects almost every single training dot by wildly weaving up and down. This is called overfitting. The map has memorized the training data so perfectly that if you give it a new, real-world data point, it's going to wildly miss the mark. Simple is very often better.
So we can draw straight lines for continuous numbers, right? But what if we want a percentage? If we want to predict the exact likelihood that an email is spam, a straight line stretching off to infinity in both directions just won't work, because probabilities absolutely have to stay strictly between 0 and 1. Enter logistic regression. To solve this, we take our linear math and wrap it inside something called a standard logistic function, or a sigmoid function. This brilliantly acts like a mathematical trash compactor. It takes a line stretching to infinity and magically compresses the output into a neat, continuous S-curve bounded perfectly between 0 and 1. So now, a result of 0.85 means there's exactly an 85% probability the email is spam. Lines and curves are great for geometry, for sure. But sometimes real-world problems just don't look like dots on a scatter plot. What happens when a problem is better solved by a flowchart of distinct, logically driven decisions?
This brings us to our final algorithm, decision trees.
Here, we step away from drawing lines entirely and move into building non-parametric models by actively splitting our data. Just imagine a massive flowchart. At every branch, the algorithm has to ask a yes or no question to split the data. To decide exactly which question to ask, it relies on a concept called entropy. In this context, entropy is a measure of mathematical uncertainty. The algorithm's singular goal at every branch is to minimize this entropy, ensuring that every single split drastically reduces the chaos and uncertainty in our dataset. The algorithm will just relentlessly keep splitting the data, asking question after question, creating cleaner and cleaner subgroups. And it only stops when it hits one of these constraints. Either the remaining group is perfectly classified, it simply runs out of questions to ask, the entropy reduction isn't really worth the effort anymore, or it hits a maximum depth limit that we set. What you're left with is a highly structured, easily readable map of predictions. We've seen the raw mechanics today, from maximizing margins to minimizing squared errors to reducing entropy. The crucial takeaway is that machines absolutely do not learn. They're just a mirror, relentlessly reflecting optimized math back at us based entirely on the data we give them. Which leaves you with one final deeply important question. If the machine is just optimizing data, whose truth are they actually optimizing? If the spreadsheet is fundamentally flawed or incomplete, the math is just going to perfectly optimize those flaws. Are we actually building intelligence or just incredibly complex mirrors reflecting our own data back at us? Something to think about. Thanks for joining me on this explainer, and I'll catch you on the next one.